Hello, everyone. I am Professor Hua from the Communication Engineering Teaching and Research section at Wuzhou University, and welcome you to this mini lecture. Today we will cover Chapter 1, Section 2, Determination of System Linearity and Time Invariance. Next, we will begin with the first topic of this session, the question of determining whether a system is linear. In a previous section, we stated that systems can be classified as linear systems and nonlinear systems. A linear system is one that exhibits linearity, which comprises both homogeneity and superposition properties. Both properties must be satisfied simultaneously, or the system is nonlinear. We now introduce the homogeneity property and the superposition property separately. The homogeneity property means that if, when the system input is f of t, the output is y of t, then, when the system input is k times f of t, the system output correspondingly becomes k times y of t. When a system satisfies the above condition, it is said to satisfy the homogeneity property. Here, k is a rational constant. The superposition property means that if, when the system input is f1 of t, the output is y1 of t, and when the input is f2 of t, the output is y2 of t, then, when the system input is f1 of t plus f2 of t, the system output correspondingly becomes y1 of t plus y2 of t. When a system satisfies the above condition, it is said to satisfy the superposition property. We have introduced and explained the homogeneity property and the superposition property separately above. Now, we will combine these two properties into a single representation. A continuous time system with linear properties can be expressed by the following two equations, where alpha and beta are arbitrary constants. Furthermore, to express a system's linear properties more clearly, one can also use a block diagram as shown in the figure, under the premise that input f1 of t gives output y1 of t, and input f2 of t gives output y2 of t. Then, for input alpha times f1 of t plus beta times f2 of t, the system output is alpha times y1 t plus beta times y2 of t. By the same token, the linearity of a discrete time system can be judged using the above method. The linearity test for discrete time systems could be expressed by. In addition, the mathematical model of a linear system is primarily represented by a linear differential equation or a linear difference equation. A linear continuous time system is described by a linear differential equation, while a linear discrete time system is described by a linear difference equation. We will discuss issues related to differential equations and difference equations of systems in detail in Chapter 3. Next, we will illustrate the problem of determining system linearity with examples. Please look at example 1 and determine whether the following systems are linear systems. Here, f of t is the system input, also called the excitation, and y of t is the system output, also called the response. Zu Problem 1. The system input is f of t, and the output is y of t equals 4f of t. This simultaneously satisfies the homogeneity property and the superposition property. So, it is the linear system. Zu Problem 2. The system input is f of t, and the output is y of t equals 6 times the square of f of t. This does not satisfy the homogeneity property, so it is the nonlinear system. Zu Problem 3. The system input is f of t, and the output is y of t equals 4 times the square of f of t plus 3f of t. This does not satisfy the homogeneity property, so it is the nonlinear system. Zu Problem 4. The system input is f of t, and the output is y of t equals 3f of t, plus 2 times the derivative of f of t. This satisfies the homogeneity property and the superposition property. So, is the linear system. From the analysis of the 4 systems above, we can see that a linear system must satisfy the homogeneity property and the superposition property simultaneously. Otherwise, it is a nonlinear system. Next, we turn to the second topic of this session, the problem of determining a system's time variance. In a previous class, we said that the third way to classify systems is into time-invariant systems and time-varying systems. As can be seen from the figure below, if a certain system has input f of t and output y of t, then when a signal is delayed by t0 before passing through the system, its waveform shows no change compared with the undelayed case, and the input delay and the output delay are equal. In this case, we call such a system time-invariant or a non-time-varying system. In summary, if the relationship between a system's output and input does not change with the starting time at which the input signal acts on the system is called time-invariant. Otherwise, it is time-varying. The mathematical expressions for a system's time variance are given below. The 2 lines above express time invariance for continuous time systems, and the 2 lines below express time invariance for discrete time systems. Note that the delay of a continuous time system is denoted by an arbitrary constant t0, whereas the delay of a discrete time system is denoted by an arbitrary integer n. In addition, the mathematical model of a linear time-invariant system is a constant coefficient linear differential equation or difference equation. A continuous time linear time-invariant system is represented by a constant coefficient linear differential equation, whereas a discrete time linear time-invariant system is represented by a constant coefficient difference equation. Next, we will illustrate the determination of time variance with examples. To deepen your understanding of this issue, please look at example 2 and determine whether the following continuous time systems are time-invariant systems, where f of t is the system input and y of t is the system output. Subproblem 1. The system input is f of t, and the output y of t is the sine of f of t. When the input f of t becomes f of t minus t0, the corresponding output y of t becomes sine of f of t minus t0, which equals y of t minus t0. So this is the time-invariant system. Subproblem 2. The system input is f of t, and the output y of t is the product of f of t and cos t. When the input f of t becomes f of t minus t0, the corresponding output y of t becomes cos t times f of t minus t0, which is not equal to y of t minus t0. So this is the time-varying system. Subproblem 3. The system input is f of t, and the output y of t is 4 times f of t squared plus 3f of t. When the input f of t becomes f of t minus t0, the corresponding output y of t becomes y of t minus t0. So this is the time-invariant system. Subproblem 4. The system input is f of t, and the output y of t is 2t times f of t. When the input f of t becomes f of t minus t0, the corresponding output y of t becomes 2t times f of t minus t0, which is not equal to y of t minus t0. So this is the time-varying system. From the analysis of the 4 systems above, we can see that for a time-invariant system, when the input is f of t minus t0, the output must equal y of t minus t0. Otherwise, is a time-varying system. In addition, please note that time invariance considers only the zero-state response of the system. Therefore, when judging the system's time invariance, we do not involve or consider the system's initial state. In other words, for systems with initial states, the above method cannot be used to determine time variance or time invariance. Please reflect on today's lecture and complete the following homework exercises to consolidate the concepts learned and deepen your understanding. This concludes this session. See you in the next mini lecture.